Hello, good afternoon, everyone. I guess we can start. My name is Sergio Albani. It's a pleasure for me to co-chair this session on GeoAI and Geospatial intelligence, together with Professor Evelyn Uema. My background is in physics and Earth observation research. Much of my work has been on the intersection of science, technology, and policy. So the focus of this session takes us to one of the most dynamic frontiers of our field. That's the convergence of Earth observation and artificial intelligence. And this is more than a technical development. It is basically changing the way we turn data into knowledge and knowledge into action. So we are moving towards systems that are scalable, interoperable, and explainable, capable of extracting value from the huge volume of data now available. The opportunities are significant, from monitoring land cover and the biomass to supporting climate resilience, sustainable resources, and security. At the same time, we face a number of key questions. How do we ensure transparency and trust? How do we design infrastructure that are open and interoperable? And how do we balance automation with the human expertise? So these questions are not only scientific, they are also strategic, and they connect directly to Europe's vision of digital infrastructures and data spaces that serve both research and policy. So the presentation in this session contributes to that vision, showing how GeoAI can be made operational, reproducible, and impactful. So with this perspective, I invite you to listen not only to the methods, but also to the broader implications, how these innovations can help us build a responsible and trustworthy GeoAI for Europe and for the global community. So thank you for being here. I guess we can start. Let's begin with the first presentation. Our first speaker is Omar Barrilero from SATSEN, who will present exploitation of knowledge graph technologies for geospatial intelligence use cases. Omar, the floor is yours.
Thank you, Sergio. Hi, everyone. I'm going to present the work that we have been doing for the exploitation of knowledge graph technologies for the geospatial intelligence use cases. This is something that we have made in the context of an European project, the ENEXA project, that it is a project that just finished a couple of days ago. And the main objective of this project was to be able to provide technologies that allow us to work with what we call real-world knowledge graphs. So it's basically big knowledge graph, the order of more than 1 billion of triples, putting also the focus on the explainability of the methods that we can develop with them. So first of all, as I'm not sure if you're very familiar with the concept of knowledge graph, a very brief introduction is that a knowledge graph is a way of representing the information, that it is basically representing the information as a set of collection of nodes, entities, and relation between them. So the basic statement for this knowledge graph are what we call the triples, that are basically an object, predicate, a subject, predicate, an object. So, for example, in the graph that we have here, we can see that Lily is interested in Da Vinci. So we have these three concepts: the subject, the predicate, and the object. And with this information, we can build all this knowledge and all these interlinked connections. So this basic statement is what we call triples. And also we have this Sparkle language, that it is the query language that we use for querying questions to these knowledge graphs. So based on this, we are developing these use cases based on this Nexa technology. So I would like to start doing a summary of which are the technologies that we are using and I'm going to present to you during this presentation. So besides Nexa has more than these technologies, we're going to focus on only these four: the extraction module, the knowledge graph embeddings, the triple storage, and the class expression learning, that are the ones that we have been using in our use cases. So first of all, and the most easy to understand module is the extraction module. Is basically, we know that we need to work with a lot of different data, that it could be in text, it could be in structured data, it could be in images. And the idea is that if we want to work with knowledge graph, we have to be able to extract this information from these data sources and to transform into triples. So basically, we have models for doing that. There are more simple or more complex depending on the data. For example, when we work with text data, we need to apply language models to do that. But the final objective is to transform all this data in triples. Then the two main challenges when working with these extraction models is to, first of all, we have to put the focus on the entity linking. So one of the examples that we had before is we have a triple that it is that we have a flood that affected Maradi. This means that this flood affected Maradi, but what is Maradi? If we are able to make this entity linking and being able that, this Maradi is this identifier in a Wikidata knowledge graph, for example, then we can link all this other information that we know about this Maradi concept. So we know which is the population, we know which is the elevation, which is the country. So if we are able, when we do the extraction module, when we are extracting the information, we are able to link with these other data sets. We are introducing all this information in our own data sets. And then the other main challenge was the importance of management spatial data. So as we are working with data that is very related to the geospatial domain, it is very important its location and the relations between this data. So basically, it is important to include in the knowledge graph the information to be able to make relations and geospatial functions with these different data. So basically, we can have different approaches. We can use triple stores that we selected that are able to provide these geospatial functions. But it is also possible to define which are these relations explicitly in the graph to make it more efficient. In this case, instead of using this relation between the different concepts, what we have done is to make relations of all the concepts that we put in the graph with a common grid, so we can have these specific spatial relations with the elements. The next module, I already anticipated, this is the triple storage, is the way that we are storing all the data. There are different solutions like GraphDB, Virtuoso, but in the context of the project, our partner of University of Padua developed a solution that it is Tentris, that it is very important to us because it allows us to represent in a very efficient way the knowledge graph. So we are talking that we are going to be working with knowledge graph of more than 1 billion triples, so the efficiency is key for us. And the idea is to represent these as tensors using hypertries. So I'm not going to give much more details on this, but if you are interested, we can talk later about that. Then the other module is about the knowledge graph embeddings, to generate embeddings for the different entities in the knowledge graph. I'm not going to explain about the embeddings because I think it's the concept I have here the most from the beginning of the conference. And finally is the class expression learning. So this is a module that it is quite interesting for the demonstrator that we have built, is that what is a class expression is that when you have a lot of different entities, you can try to find in this knowledge graph which are the characteristics that these elements have. So we have these different rules and different connections in the knowledge graph, and it is possible using this module that, I have these different entities. I know that for example, these three are fulfilling some characteristics, or there are real area strips, for example, and these other ones are not the area strips. So it is able, this module, to find which are the entities and the characteristics that they have in common, these different entities. So this is a model where we can provide positive and negative examples of the things that we are looking for, the things that we're going to classify, and the model is going to be able to provide us the rules for classifying these models based on these examples. So why we are participating in this project is because we are interested in exploring these technologies in the GeoInt domain, mainly because we have in the GeoInt some specific challenges that we think that could benefit from the outcomes of NEXA. One of them is the data heterogeneity. In the geospatial domain, we have to work with a lot of different data that has different formats that are in different silos and so on. So basically, knowledge graph allows us to have a very flexible integration of this knowledge. Then also, we have a limited use of contextual information. Typically, when we have, for example, models for area strip detection or for rock detection, we are typically just relying on the information that we get in the images, but we are not using more information about the surroundings or even conflicts that happened in the past or these kind of things. So the idea is to be able to integrate also this contextual information in our machine learning algorithms. And finally, also using this classification learning is that we are going to be able to not have this machine learning just like black boxes, but to have some kind of rules that are understandable and can provide a kind of explainability for the models. So with this in mind, we define two main applications or demonstrators. One is about the integration of multiple and heterogeneous sources. So basically, we have focused on the analysis of natural hazards. So we're integrating in a big knowledge graph a lot of different data sources and expose this to the users in an easy way to explore this data. And the other is related to the relevant change detection. For the first one, we have integrated in this knowledge graph that it is more than, I think it's 1.1 billion triples. We have integrated information about these natural hazards events from different sources, OpenStreetMap data, also the metadata from the Copernicus imagery, Sentinel-1 and Sentinel-2 in particular, land cover, and also information about conflicts and migration data. The idea is to enable the users to make easy relations with all this data. And then what we have provided is some very easy to use interfaces with some Jupyter notebooks where the user can interact and make some queries in an easy way that they can extract information from the knowledge graph. For example, here we have some statistics about the events of the flooding events that happen in Niger in some period, or the conflict that we have in Afghanistan, also using different colors for the different number of affected people. This is just exploiting only one of the data sets that we have integrated, but it is also possible to make more complex queries to the knowledge graph, like, for example, provide a list of a number of Sentinel-2 images without clouds in the year 2021 that have been acquired over an airport, or that have been acquired after a flooding, or that have been acquired in the 3 following days after a flooding that it is affecting to 100 people. So we can try to merge all this information that we have in the knowledge graph to provide all this information to the users. So they can merge all this information to make these advanced queries. So this was the first application. And the second application is related to the relevant change detection. This is an application that we have integrated in our Geospatial platform in GeoDam. And basically, the final objective of this is to be able to monitor some areas. In particular, we're working there in Amazon, and to identify new deforested areas that could be possible illegal mining sites. So this is an application that happened in 2 steps. So in the first step, we're improving some detection algorithms that we have. So we have some algorithms for man-made structures. So typically, for example, in this case, we have developed airstrips, roads, and buildings detectors. This is the traditional approach for building these detectors. Basically, the traditional approach is you collect the data, you pre-process the data, you make the annotations, and then you can try to train a model for detecting this. What we are adding with Nexa is that, okay, we do exactly the same at the beginning, but finally, when we have these detections, for every detection that we are having, we add this contextual information about, for example, the number of buildings that we have in the surrounding, or the distance to the rivers, distance to villages, or all the kind of information that we think that could be interesting. We add this information in a knowledge graph, and then provide this information to the class expression learning. So when we have all this contextual information, we can provide, when in the original detection we can have false positive and true positive, we can provide these positive and negative examples to the class expression learning, and we have these improved detections based on these rules that the class expression learning can learn from this. For example, they can say that, okay, if I know that the land cover typically is most of the year is water, this is not an airstrip, it is something that your model has made wrong. So it is a framework that allows us to improve these fault detections in our models. And then the second step for this application is that, okay, once we have already this improved feature detection, we can launch our algorithms for the deforested areas monitoring. We're using Sentinel-1 or Sentinel-2. When we detect an area with deforestation, we can run this improved feature detection algorithm. So we are detecting the airstrips, the roads, or the buildings. We are adding more contextual information to this area, like, for example, the type of territory, the number of conflicts in the surrounding, the distance to different cities and villages. We apply, again, this class expression learning to get the rules. And then, using positive and negative examples of legal or illegal mining sites, we are able to differentiate between them with the rules learned by these models. So basically, this is how the application looks like. So basically, the user can just select an area in the map, define which are the time where we want to run the algorithms, if we want to include in the analysis the strips or so whatever, and then just click a button, and all these models happen in the backend, and finally, we are going to have the results. So I'm going to finish already with my conclusions that we see after this test and the build of this demonstrator that these knowledge graph technologies allow very well this flexible integration of huge amount of data and facilitate all the research on complex things of this data. But also it is very important the reliability of data. So there are a lot of data sources, but in order to be sure that what we are getting has an added value, we have to put the focus on be sure that the data that we are putting there in the knowledge graph is reliable. And then also we notice that the enhancements of machine learning algorithms is good. It's mainly depending on the kind of algorithms. When you have these algorithms that we don't have a lot of very big training data sets, because in the security domain this is the case typically, these models allow us to improve them very easily and also allow this kind of explainability, providing these explicit rules that we can provide to the operational analyst to understand if they are right or not. And for future evolutions, we are considering adding attack optimizations for these different modules, like, for example, not working with the global knowledge graph, but for the specific areas with the specific data, depending on the usage. And also, in order to facilitate the exploitation of the knowledge graph, to include the possibility of running natural language queries. Right now, what we are doing is we have some templates of Sparkle queries that the user can interact easily with combos and so on. But the idea at the end should be the user can directly, with natural language, ask queries to the graph to get the results. And that's all from my side. Thank you. I don't know if you have any questions.
So thank you very much, Omar. I guess we have time for one question. Anybody? There's a person there.
Yeah, thank you for your talk. I was wondering, you didn't mention, usually when we hear talking about RDF and knowledge graphs, usually people mention ontologies. So I was wondering if you are using specific ontology. Have you defined some specific ontology to structure your knowledge graph models? And
yeah, we have.
So if there are, was wondering, I don't know that well the ontologies for this domain, but maybe there are some open ontologies that you could have reused also?
Yes, basically for the first demonstrator that we did, this knowledge graph with the natural hazards, we are building on the ontology of, I think it was World Knowledge Graph, that it was a knowledge graph for events, that it is publicly available. And then we have made some adaptations that are available in the project, in the Nexa project. So basically, the idea is to be able to build on the existing ontologies and not reinvent the wheel, of course.
Okay.
Thank you.
Okay, thank you very much, Omar.
Thank you.
So we can go for the next speaker. It's Vytautas Jankauskas from DLR. The presentation is on Grumblick AI-powered forest biomass estimation service. The floor is yours.
Hello. So, hello, my name is Vytautas. I work at the Data Science for Earth Observation Department at the Earth Observation Center in the German Aerospace Center, or DLR. The goal of our department is to apply state-of-the-art data science and machine learning methods to satellite data in order to solve various societal challenges. So the work we do is incredibly diverse. How do I switch slides? Okay. So one of those projects is called Grünblick. It was a project with in the beginning an industrial partner, and currently we're looking for a new industrial partner. And the goal of the project was to provide a biomass estimation service for, so originally for forest inventory uses. So this company had owned forest in Austria, I think, and they're interested in estimating the biomass of said forest. So, yeah. The idea was to develop a sort of modular, scalable pipeline that incorporates training, inference, as well as interactive user service that would allow people to retrieve biomass estimates on demand. Yeah. So above ground biomass is an estimate of how much mass is there above ground. In this case, we're interested in forest mass. So forest biomass estimation is crucial for things like climate change mitigation, biodiversity assessments, forest management, and so on. And of course, as in many things, remote sensing, AI, and big data are contributing to the field tremendously. Yeah, so in Grünblick currently we integrate Sentinel 1 and 2 data along with deep learning for precise scalable forest biomass estimation. So the Grünblick service consists of a website where a user can specify area of interest. A deep learning model can calculate the biomass, and it's then made available to the user for download. Part of this is we also interface with various services for satellite data retrieval, well, various APIs, so Stack, Google Earth Engine, and so on, in order to retrieve data for training. The pre-calculated biomass is cached in order to make this feasible. Yeah. So that's the sort of conceptual diagram of the service that we've been developing. The main components are as I mentioned, the retrieval service and the machine learning model and inference models. As of now, the model we've used for this is UNet with swappable backbones for, swappable encoders. And my colleagues prepared some experiments to justify this choice. So, yeah, as I said, the idea is for the user to specify an area and retrieve the. For the training of the models, we used one existing data set. So we used the Biomasters data set from Finland, which is derived from LiDAR data. So that's a publicly available data set. But we also compiled our own data set. So we took the data so the regional government of British Columbia and Canada made available an archive of shape files for the whole area of British Columbia, where each shape has many different biomass criteria or attributes associated with it. So we rasterized this data. We sampled randomly the area, and then we retrieved the corresponding Sentinel 1 and 2 patches for that area and that time in order to compile our own data set. Yeah, it's basically just to increase the robustness of this service. And one of the main goals of the service is to also allow people to easily incorporate new sources of data and potentially even new modalities. Yeah. So we did some experiments. So the service doesn't rely necessarily on any particular machine learning model or deep learning model, but currently we used UNet with, so we've experimented with different encoder backbones. So currently the efficient net B0 seems to be performing the best. We've also experimented with some self-supervised pre-training. We used the SSL4EO pre-trained model for this purpose, which also seems to improve the accuracy of the model. And yeah, unsurprisingly, so we also tried using just the Sentinel-1, Sentinel-2, or the data sources fused. So unsurprisingly, using both increases the accuracy. And as of now, our current work is to make the service more scalable, as well to equip it with some uncertainty quantification capabilities, yeah, to have a robust and reliable service. Yeah, so these are some results, and that's it from.
Okay, thank you very much. Any questions? This one there.
Hi, I have a question. If the images can be used to determine if, for example, the trees are getting fragmented, there's species, for example, falling sick or ceasing to exist for whatever reasons, and can those images be useful in catching it early on?
So, well, with Sentinel-2, not really, because the resolution is 10 meters, so you're limited quite a lot in the optical. Yeah, but obviously something like this can be developed for other purposes too, but higher resolution data would be needed here, right? Or maybe a different modality, like, I don't know, LiDAR or something.
Okay, any other questions? No? I have one actually, if I can. So biomass monitoring clearly can support climate policy and carbon accounting. So how do you see services like Grumblick being connected to European policy framework such as I don't know, the Green Deal or also national obligations?
Okay. I haven't thought about such a high-level policy questions yet, but obviously, if someone is interested, we could collaborate with to provide information or data or services to interested parties. But yeah. Or do you have anything specific in mind?
It was just a reflection. So I cannot see anyone with other questions, so thank you very much.
Thank you.
We can go for the next speaker. That's Jadon Duzella from the Technische Universität of Berlin, and he will be presenting automating Earth observation analytics pipelines with Agent Raven. Jadon, the floor is yours.
That's not my presentation, I'm afraid. I've uploaded them.
Problems with your presentation. So Sorry about that. Maybe we can go over with the following speaker while you can try to solve the situation.
So the next speaker will be, right now we do a swap. So we will actually switch to the next presentation. That would be Michael Jendricke from GeoInsights, talking about how we can increase interoperability via DGGS.
Waiting for my slides. Because that was my slide before, so. Wonderful. So, hello everyone. I'm Michael, co-founder at GeoInsight. And I'm going to present a very wide-ranging topic here. It is about interoperable data economy, which is a big term in itself, to enable GeoAI via spatial tokenizers. Big words. I'm trying to break it down into a story. And that story starts with a slight introduction about what geodata we have available and what the problems are and how to get to a GeoAI. I'm talking about interoperable data spaces. What is a data space? A couple of definitions with boring slides and text, and how we can connect these data spaces to an AI. Then the concept that I'm introducing is this spatial tokenization, or DGGS. I'm going into a couple of use cases and implementations. That's really where the rubber hits the road, how to enable this GeoAI that we all want, I presume. And at the end, an outlook, what the future may look like. Okay, an introduction. So we have big geodata, obviously, but it's costly to store, it is messy, it comes in all kinds of projections, formats, and so on and so forth. But we do not only have data from space. We have data from IoT devices. We have data from social media that is geo-referenced. We have data from traditional maps, from other maps. We have data coming from weather stations and so on and so forth. And all this should be integrated to have a complete picture of the surface of the Earth and what is going on in order to run a fully fledged GeoAI. Interoperable data spaces. I just put these definitions here, don't read them. What they all sort of come at is it's sort of a decentralized space where data is stored and exchanged between actors. You have participants that want secure and trusted data, which is interoperable based on standards. So there are many concepts like this that are existing, like the Copernicus data space ecosystem. You're familiar with that, probably. You have sort of European policies like, or ideas, or I would call it the wish list, like Interoperable Europe Act, which is focusing on the exchange of data requiring seamless interoperability. You have the Simple program, also from the European Commission, that is supposed to be secure, interoperable with open source components to use and leverage existing data and build data chains. You have GaiaX, maybe you heard about this. This is so half existing. There the focus is on having it federated where users can retain their control over the data, and it's meant to be an ecosystem to drive the European data economy of tomorrow. That kind of got stalled, the GaiaX. So we have data spaces out there. They all have sort of their own mechanisms and standards how data is provided. How do we connect these data spaces to an AI? And on purpose, I dropped the geo, because our community always has the issue that it always needs to be geo. There's always geo in front, but we need to get out of that bubble and just serve sort of the AI or analytics community as such. One thing, for example, the Simple program that I mentioned, they dropped geo entirely. They don't consider it part of an infrastructure. They think geo is a plugin later on. So that's a risk for us. So how do we serve that AI community? We know one data space is great. You can run an AI based on that. Multiple data spaces with all their formats and APIs become already a problem if you want to run AI on that. And so the term that the AI community or GeoAI community came up with is spatial tokenization. How do we take this data and reference it to little buckets, to little tokens, to little containers? And with that, we could open the tab to this data and allow AI algorithms, advanced statistics, to always reference the same location on the surface of the Earth. How does that work? Spatial tokenization. This is the concept behind it. This is a discrete global grid system. You have heard it in a couple of talks already. It is this hierarchical partitioning of the surface of the Earth into, in this case, hexagonal cells that are almost equal size. And it always allows you to reference a particular place on the surface of the Earth with an ID. And if you cringe at the term spatial tokenization because you're familiar with grid systems, that's okay. That term did not come from me. That term came from the GeoAI folks. I will skip that because that's the definitions of what a grid is, what a cell is. There's a lot of talk about it. What you can remember is sort of you have an area that is representing a space, a region on the surface of the Earth, and is always the same when you give it an ID. You always get the same zone back. Imagine it like this. We have the lat long space. Is it analog or is it digital discrete already? Essentially, you can have that point anywhere on the surface, right? For me, that's sort of an analog space in the sense that you can be, to the precision of your float, you could be anywhere. And the way this tokenization now works is you take that location and you encode it with the zone ID. So that's this red to yellowish green path on the top. You go, and what you get is a zone ID. And that zone ID is also the representation. If you go back and you decode that, it would be represented as a zone in your map again. You have compact hexagonal zones of equal size. In that case, there are many different grid systems. We don't know which one is the best. This is just one of them. And one of the huge advantages of these systems and how we can reduce the load in terms of processing and in terms of making it efficient is you have it in hierarchy, right? You have parent zones that have subzones or children, and you can sort of take the grid system, run it on the entire planet or on all of Europe, and figure out the zones that have a signal that you're interested in, and then only focus on these zones. You disregard the rest. And that hierarchy is super powerful if you want to do large-scale analysis and then break it down to a particular location. Use cases. We have done that here for California, where we took fire incidents. We placed these fire incidents in these zones, and you can retrieve information about these locations, and you kind of build up a digital fingerprint of these zones by putting and adding more and more data to it. Here's an example of canopy height in Belgium at a higher resolution. And here's the global population layer, also in hexagonal cells covering the entire planet. Because we got the reply often from people that are working in very high resolution based on fields and agriculture, this does not work. DGGS is not a suitable solution for us. It's too coarse. No, you can have zones that are basically centimeter scale, and you can cover an entire field with many zones and even have details within these fields. Here's an example of different sort of vegetation health indices computed directly in the grid zones. Here's an example that I did a while back. which is hate crimes in the US. What did I do? I took continental USA and I loaded to the zones over 400 parameters about demography, about economic status, veteran status, for example, social statistics, and so on and so forth. And I had a layer that told me where a particular type of crime, hate crimes, occurred. And then I built an artificial neural network. And I asked it basically, okay, based on these input crimes, what do you see as the map that comes out of it as a prediction where these types of crimes could also occur? And interestingly, this is what the computer came up with, and it fit the literature. There's no way to really validate that, but the literature said hate crimes occur there where people from one group move into an area of another group, so at these boundaries. And this is exactly what the algorithm also figured out. Implementations. So because we have this sort of as a very academic concept for long while, these DGGS systems, what are the implementations that we need to move this forward? One of the big hurdles at the moment is that you cannot easily visualize these zones in a traditional GIS system. That is because they're not DGGS aware. They don't know what that zone ID means, what the geometry looks like. So having a system that can read zone IDs and represent the geometry of that zone, that's important, and this is what we're working towards. One of the projects is called GeoPlagma. That is an open source DGGS library that is collecting many grids. You can think of GeoPlagma as the PROJ project of DGGS, and it will give you these spatial tokens, and it will give it to you consistently. We will implement tests for that so that we always can be sure that zone ID belongs to that zone geometry. Currently, we are also working on a DGGS API to have this sort of functional as a web service, and we're involved in the AI and DGGS pilot by OGC. And one of the things that my co-founder Joao yesterday presented in the demo is DGGS.io. That is similar to GeoJSON.io, where we want to give users the ability to take their data, put it in that system, and get it back as zones. You can then hopefully, in some future, drop your cloud-optimized GeoTIFF and get the zones back. There's a working prototype at this moment, but it will be extended to also download, that you can download Parquet files or GeoJSON files. Outlook. Right now, and this is really for us where we are at this point. Cloudflare has the entire Copernicus data available on their servers, right? So we attach to their infrastructure. And what we want to do now is put our API there so that you can download any of the Copernicus data sets in any of the grids that we support via that API. That will give you the entire archive in spatial tokens. Another point where we have touch points is with the CEO's analysis-ready data. They are thinking about these grid systems in a very similar sense. They see that all the images come sort of with their own local grid system. How do we harmonize that into a grid system that is consistent? And DGGS is a solution, and they're thinking in that direction. So this would be super far in the future. I'm hoping that at some point our sensors, the satellites themselves, collect data not in these pixels like today, but in pixel zones. And they acquire them, and the same zone ID that the sensor knows where it is, also the user sees on their screen. That's sort of the, yeah, maybe 2 or 3 decades in the future. That will be sort of where this concept could be implemented. And that's it. The QR code is the demo that we have. Check that out, and I'm happy to answer questions. Thank you.
Thank you. Questions? I have a question until others are thinking. I really like the idea of DGS supporting sort of AI, because it really is, you know, making the data really quickly available for that. But DGS, there are many DGSs.
Yeah.
So do you see that as a problem or not right now?
I see that as a huge problem. There are many DGSs out there. There are some that get pushed, but the push to certain DGSs is often because the tooling is there. They use it because the tooling is there. HerePix is one of the examples. The way we approach that API is to be grid agnostic. So we want to support many grids, and that transformation, for example, to the Copernicus archive should happen. You can change your grid, because what we need to do is benchmarking of these grids, right? Because some grids may be useful for some use cases compared to other use cases. So some ranking, or at least recommendations, what should be used for what use case and what scenario, that is important. And I think there will be a transition phase where different grids are tested until we sort of all hone in, and it may be further in the future until, for example, ESA or Copernicus data is stored natively in this format. It would be nice to see that, but there will be a transition phase where we need to experiment.
Okay, as we are running out of time, then thank you.
Thank you.
And okay, and then we move to the next speaker, who would be, do we do the, yeah, so Gerion Dusella from Technical University of Berlin, automating Earth observation analytics pipelines with Agent Raven.
Yeah, thank you very much, and thank you for the second introduction, Arthur, this time. Yeah, so I guess in your work, you all have encountered a situation where you have a seemingly small task. You run it on system A, and it feels like it takes a fortnight. And then you switch to system B, and it feels like you turned the speed up to 11. And then you probably think, well, if I just would have known before, wouldn't it be nice if there was just some oracle, some agent that would tell me which system to choose? Well, traditionally, an optimizer inside a data management system would fill this role. As inputs, it uses the workload or query and data set, including the metadata. Then it optimizes how that will be processed, and then it sends this to the execution engine, which in turn will return the result eventually. However, a traditional optimizer needs well-structured data, and it needs to understand the system in order to optimize, or it wants to optimize for very well in order to do its job properly. Additionally, a traditional optimizer would usually focus only on a single data management system. So what we propose in our work, in our vision, is using an AI agent for optimizing Earth observation queries between different systems. Specifically, we propose to use one AI agent just for zonal statistics queries. That leaves us with 3 somewhat easy questions to answer. First, what are zonal statistics? Second, a bit harder, how does our proposed system work? And third, why do we believe that one single operator, like a zonal statistics operator, is the correct size for a dedicated AI agent? Let's come to the first. What are zonal statistics? And I guess most of you already know, but for those who don't, a quick recap. A zonal statistic is a way of aggregating the values of all raster pixels that are masked by a certain value within those vector features, and then we do this for all requested vector features at once without doing it like separately. So given a raster and a vector data set, like a map of forests and some cadastral data, we can mask the raster and aggregate the pixels to then know which of the plots of land the forests contain. In this case, we get a table as a result that shows how many pixels per plot of land contain forest and how many don't. But even for this comparably small query, we have to manage a lot of parameters that will impact not only our result, but also our performance or latency. There are more obvious ones like which data sets to load or which vector features to select, which functions to aggregate with. Then there are like less obvious ones that are about calculating the mask, what function to use for that. And then there are the hidden ones that only really impact the system internally, like the tile size, the internal tile size, or the choice of the coordinate reference system. And as usual, like we have to provide these parameters to the spatial system somehow. But what now? One of the optimization parameters is also which system to choose. Then we also need to learn about the systems on top of tweaking the parameters. And this can lead to quite a bit of linguistic clutter. For example, here what we show is for 4 different systems, for PostGIS, for Beast, for Sedona, and for Rasterman, their queries of representing a zonal statistics query. If we now take our parameter classes that I just introduced and we overlay them over those queries, we can see that essentially every system uses a different structure in their queries. This makes it hard to switch between systems. To alleviate this, we at first introduced, or we built Raven, our system for unifying zonal statistics. With Raven, we can run queries in a system agnostic manner and can switch between those different systems very easily. We can configure it flexibly, and then we can apply easy optimizations, also to a certain degree automatic, and we also can compare the systems as we store everything. In Raven, a query is structured very focused on what zonal statistics queries need. First, we define the data set, then the aggregation operations, the system we want to run on, and then any parameters that we actually that would actually implement or influence how fast the query runs. Internally, what Raven does is the following. First, Raven reads the query with a pipeline planner, which forwards it as an internal representation to the execution interface. Then we take the data sets, of which Raven already knows the metadata from, as it has seen them before. And we put this into the preprocessor, which aligns the data sets and converts them such that the query can run most efficiently on the spatial system, which the execution interface sends the query to. Then the spatial system runs the query and returns the result. And while all this happens, we record metrics to store in our zonal statistics database. So why and how could an agentic system now help us in our optimization scenario? Well, let's quickly define first what an AI agent is. An AI agent to us is a system that perceives its environment, reasons about goals, and acts autonomously to fulfill user requests. Hereby, we separate between single agentic systems, which would only interact with themselves and with the user, and multi-agentic systems, where the agent can also communicate with other agents on its own behalf during using well-defined interfaces. Our vision for Agent Raven is now a multi-agentic one, where we imagine the following extensions. First, we have our zonal statistics agent, where also to which also the user would communicate. And this agent takes the queries and sends them to the Raven execution environment. The zonal statistics agent also reads from the zonal statistics database to get information on past queries. The agent then would send instructions to the deployment agent, which in turn would deploy the spatial system and also take care of the zonal statistics agent still running. And third, we have a dataset discovery agent, which would now provide the datasets. How would now a multi-query optimization look like? This is our main focus here. Well, let's look at a quick example. Here we have a user submitting a query that requires certain datasets. At first, Agent Raven will take those data sets, analyze them, and optimize the internal plan and instruct the deployment agent to start the correct spatial system, in this case, a database management system. The system is now instructed to load data sets, run the query, and return the results. If we now have a second query, then at first the process is the same. Raven analyzes analyzes the data sets and now has to decide, as one of the two data sets is the same as in the previous query, should it submit the query to the first spatial system, or, and that's the other option, should it start a second system and run the query there if it deems this faster? Okay, so I hope I could convince you that even something seemingly simple, like a zonal statistics operation, can be quite complex. In fact, it can be so complex that it justifies not only optimization, but because of the nature of the query and the typical workloads we observe, it also is useful to think about multi-query optimization. This is where in the future our agent Raven will come in and or will climb in and take out the guesswork for system choice when running zonal statistics queries. And now I'm happy to take any questions.
Thank you. Questions? I have a question. How would you ensure, or what would you recommend that those workflows, automated workflows, would be transparent so that people would trust sort of into the system? Because right now you have like an agent, if I understood correctly, and
you mean how user would, in what sense trust the?
Sort of that, I mean, I understand that you build like, there is an agent that person then only interacts with the agent, that then behind the scene there is some automated workflow happening that if I use it, that I would kind of trust that, okay, whatever it comes out is actually true, especially if working also with different databases. You brought an even example that sometimes those also don't align. How would you deal with that?
So there is a theory and there's a practice answer. Like the theory answer is it shouldn't matter. This is why we have optimizers, and optimizers for us decide how internally something should work, something should be run, and it should return the correct result. Obviously, what we will need to do, and what we're to a certain degree also doing already, is looking at how similar are really the results between those different systems, because we actually observe differences in how they interpret zonal statistics query, and obviously this needs to be taken into account. But yeah, this is kind of, or in this case, it would be kind of also something for more future work, because we know there is differences. We know that there can be like very large, they can also be very small. What we probably would do in the end is we have some, we can think about some parameters that we can check after the query has run on the result in order to ensure that the result is correct enough, hopefully. But yeah, this indeed is a problem.
Any other questions? If not, then thank you. And we move on to the next speaker, who would be Peter Kempeneers, speaking about LLM-ready spatial temporal data, enabling agent GeoAI with Stack.
Thank you. So my name is Peter Kempeneers. I'm with the Joint Research Center of the European Commission, and I'm going to talk about LLM-ready spatial temporal data, and more specific, how can Stack enable agentic GeoAI systems. I would like to acknowledge my co-workers, Chiara and Jonut, and I'll do the presentation today. An outline of the talk. I'll start with some objectives and then go into the architecture of the GeoAI we implemented, the experiment we did with the prototype we implemented, and then some lessons learned and conclusion. So the objective here is how Stack can enable an agentic system. And for me, what is an AI agent? How does it differ from, how is it different from a normal LLM? And that is, we've seen it already in the previous talk, but for me there is some tools. So here I talk about tools. In the previous presentation it was about other agents that can talk to each other, but what is important is that this system can independently make decisions and divide the big task into subtasks, making use of some tools. And here, so we're talking about this tool chaining. It's an orchestration of multiple tools, and as I said, breaking a complex task into subtasks. What was important in our case when we implemented the tools is that the AI agent was using some kind of a standardized way, and we're using the MCP, the Model Context Protocol, which is implemented by Anthropic. You could say it's like an emerging ad hoc or de facto standard that enables AI models and applications to interact with external data using these tools in a standardized way, let's say. So central to this study here is that we're talking about an MCP server allowing an agent to talk to stack data. This allows us, through this MCP server, that an AI agent can consult a stack catalog in a natural language, so that we can ask and query this stack catalog through the agent or through a prompt. I should have started probably here by this slide. For those not familiar, but I think most of you are with Stack. What is Stack? It's an open specification for describing geospatial information, and it facilitates working with Earth observation data, in particular, as in this case here, from different providers. So what are the Stack MCP server key features, also known as features? No, this is a typo of the slide. So I won't go into detail here, but what is important I would like to point out is that we've initiated here with software development, creating this MCP server, quite simple, but already effective. And what we would very much like is that this would be picked up by the software developer community so that it can be taken further. To my knowledge, or to our knowledge, this is the first MCP server for Stack. So we very welcome some collaboration, or even that it can be picked up by others. Although central here in this study was a Stack MCP server, what we have done also is combined it with other MCP servers. So we have 3 in total, so that we can obtain a real use case, a prototype that is really actually doing something. And that is, first of all, an MCP server that is capable of translating a nominal place on Earth, like Riga or Ispra in Italy, and convert it to coordinates, geographical coordinates, so that we can query the MCP server with some text that the location is known. And third, also quite interestingly, as we were using, or we are using, the CDSE platform to query our data, because they have, of course, as we have seen several times already in this conference, they have all the data available in Stack format, but they also have an API for processing. So what we've done also, very preliminary, but just to make this as a useful tool, to make the agent capable of accessing the processing capabilities also through an MCP server. So here is how it works. I'm not going into a real demonstration. I've done it yesterday, which turned out quite successfully, but we've seen actually it's still a prototype, and there's many hallucinations, especially in the tool of the processing, that the agent is sometimes just wrong, but sometimes it also works, like in this case where I just copied the working parts. So what can you do if I'm the one on the right, and then the agent is replying on the left. So what can you do here? It shows the different tasks you can do. The geocoding address is this nominatim MCP server. It can also search for satellite imagery, that's the Stack MCP server, and it can also perform OpenEO processes. We're using the OpenEO processing capabilities of CDSE. And then, as it's also like the LLM is, of course, then also capable, we're using Gemini 2.5. It's also capable of doing regular search on Google searches and so forth, and reason like a normal LLM. Next question. What is the most cloud-free image over Ispra, Italy? Yesterday I've done it over Riga. Acquired in June 2025 based on Sentinel-2. And it gives me this, this response here. So here we see the nominatim server into action and also the stack search. So it knows how to interpret the name of the place. It gives a bounding box for that area. It consults the MCP server for the stack MPI and gives me back this ID of the Sentinel-2 image of, what is it, 22nd of June, which has only a cloud percentage of 0.46%. Would you like to get more details about this image or perform any other task? Of course, yes, please. Calculate the vegetation image over that area. This is quite a simple OpenEO process because there is already a specific process ID available for it, but I've also tested with others where then sometimes the LLM is hallucinating, but sometimes it works. And in this case, it's quite a simple one and it works. I will start the NDVI job because it's already created the process graph. Those of you familiar with OpenEO, the interesting part here is normally in OpenEO you have the process graph as the language agnostic system in the middle. At the top end you have the front end, what can be in your language like R or Python. And then the middle part that is converted into the JSON process graph, and then it's a task of the backend to translate that into whatever language is executed by the specific backend. And so what we're doing here with this agent API is, with this agent is to not use, or it takes the place of the front end instead of us coding it into Python or into another language. It's our plain English language where we ask something, calculate an NDVI, and that language is then converted, or this prompt is then converted into the JSON, in the JSON process graph. So it's executing that job. I can ask for the job status. After maybe several times asking the same question, it comes up with, yes, the status is finished, it has progressed for 100%, and it gives me also a link to download the data. So this is what I've done. I've also done the same for, please calculate me an RGB image, which what you see on the left is for over Ispra, this image here, and the right image is the NDVI that was calculated as shown here. Of course, in the future, we would like to integrate this all in the same prompt so that you can also visualize the results and I don't need to download. But as I said, here the prototype really was about trying to make an agent that is capable of using the MCP server for the Stack API. What are the lessons learned in doing this experiment? We had several issues. The hallucination part was one of them, but this was not really about the Stack API. One of them, the first one actually, was the excessive usage of tokens. So there's, of course, we were using the free accounts, and we immediately hit the tokens limit. Another thing was the geospatial queries lead to imprecise spatial representations and introduced unnecessary steps in the workflow, and finally also inefficient and redundant API calls. So these were the first issues we've encountered, and they were relatively easy to fix by using the Stack API extensions. For example, there's a sort and the sort and fields to reduce the token usage, so that, for example, when you query the Stack API, you don't get a huge number of results, but it's already sorted. And for example, if I'm asking for the most cloud-free image, I don't get all the answers, and the token is limited. For the imprecise spatial representations, we were integrating the polygon geocoding through the Nominatim tool, which gave us precise GeoJSON polygons back. I already come to the conclusions. What we've done here is creating a prototype which demonstrates how an LLM agent can retrieve and process geospatial data exposed by a Stack catalog. And as I mentioned, for us it was important to have it MCP enabled, because in the GRC we have a bigger project ongoing where we would like to integrate and to use multiple agents that can also talk to each other, but all through a system that we call Aloha, and that is all connected through these MCP tools. Second, this feasibility study uses relatively simple queries. So of course, in the future, we would like to make it more complex. We also would like to make sure also that the hallucination gets solved. I had some interesting talks with colleagues from Vito, and so they had a good idea that after each of the steps, we should actually validate the process graph, so that would already solve quite some things. So there's a lot of work still to do. And as I mentioned, a visualization aspect would be very interesting, multi-agent orchestration, so plenty of work still for us to do. And thank you.
Thank you. Are there any questions? There is a hand.
Thank you for the interesting talk. I have a question, a philosophical question. The question, maybe you said, sorry, but how, when you submit this job, how you authenticate? It's authenticating with your user, or?
Yeah, very good question. It's not so, I mean, it's very practical. It's not so philosophical.
No, the philosophical is the other.
Okay. We had to, there was an issue. So it's for the moment, it was hard-coded in the agent. As it was just a prototype, we hard-coded the authentication in the beginning with the CDSC environment.
So every time a new user will have to hard-code this, or?
Well, in practice, I don't know. I mean, for this, we did it hard-coded, but I guess it could be done in the prompt. It could be done hard-coding, and I think there are several solutions possible.
Okay. Then, well, I don't know if it's philosophical or I don't know. I have the curiosity. What we do with the hallucinations, because maybe you notice when there is an hallucination. Maybe I'm not familiar with all this, and I will not notice. So. It's an issue, no? Because we are developing all these systems, and we know that there are hallucinations, but how we detect, no? Especially if we are not on the field.
Yes, I think I had discussed it also just previously with my colleague also, Eduardo, and he was saying something interesting, and that is probably there will be an evolution of these large language model, which are currently trained for pleasing us. And so rather than saying, I don't know, they rather come up with an answer that is hallucinating than saying, I don't know. And this is what we're seeing here. And probably there will be an evolution that this also will be solved. I think for this, how we'll tackle it, as I mentioned, we have to validate the process graph, so that there's also in OpenEO, there's a way to visualize graphically with a graph, a process graph, that you can see actually that it's actually doing what you want, but still, as you mentioned, if I don't know anything, and this is also what these type of tools are created for, like policymakers just asking something and don't want to be bothered about looking into the process graphs, I think we have to build in some of these checks and make sure that yeah, these checks will help us. But then, yeah, I think it will still be, to go back to the philosophical question, it will still be very important to think about this and try to solve it. I agree.
Very quick question.
Very quick one. Thanks a lot, Peter, for the presentation. My question is, there are lots of stack extensions that are available, so I wonder if you support those extensions in those queries. And a very quick second question. You also support OpenEO, and OpenEO has also data retrieval capabilities, also compatible with Stack. So how does it work in that case?
Okay, first, the first question. What was again? Sorry. Yeah. As I mentioned, this is like a first initiative, as I think it's the first, but not everything is implemented indeed. So what we hope is that it will be picked up, either maybe by the CDSE colleagues, maybe by Vito colleagues or other people, that all these extensions will then be also supported. For sure, it will not be already today. And then the second part was on. Sorry?
Already supports Stack. So how do you handle that situation? So the question is, you support OpenEO as well, processes, and one process of OpenEO is to retrieve data from Stack. So actually, that Stack connection is already there in OpenEO. So how do you handle this case?
I'm not sure if I understand the question correctly, but we are using the same Stack API as OpenEO is using. So I think it's accessing the same. So I don't see if there is any issue or should be any difference. But yeah, maybe we can discuss it afterwards, because I might have misunderstood your question for that. Sorry.
Okay, thank you. And we move to our last presentation by Nimrod Gibet from University of Salzburg, categorical time series based on semantic Earth observation workflows in land cover monitoring of semi-arid areas.
Yeah, thank you very much. My name is Nimrod Gibet. Thank you for the introduction. I'm from the University of Salzburg. And this is part of my master thesis that was done collaboratively with the colleagues from the University of Tübingen. And we were trying different methods, and for my part, I was tasked with testing out a categorical semantic analysis workflow to kind of see how effective it is in monitoring long-term land cover dynamics, particularly in in semi-arid regions where these changes can be very subtle. And one of the three challenges that we came across that I was trying to investigate were issues to do with the limited reproducibility of workflows, a bit of automation issues, and scalability. So my idea was to kind of develop a semantic EO workflow, which can be reproducible both in terms of processing and querying, to kind of address this traditional outcomes workflows that are very common. So the main question I was trying to answer was how effective are semantic EO workflows in kind of understanding of long-term land cover dynamics, particularly focusing on vegetation analysis, looking at intensity of vegetation intensity, seasonality dynamics, and also checking out the greenness index of the areas that we'll be testing out. And I will explain a little bit later about what the greenness index kind of entails. For the data and the tools that we used, Sentinel-2 data and Landsat 8, and we have this SIAM automatic mapper, which is we used for semantic enrichment, and semantic Python library and error 5 precipitation data to kind of understand what kind of output you are getting, because vegetation analysis and precipitation kind of are very correlated. And as a general workflow, on the left, we do have sorry, not talking. So we do have a workflow where we have the Sentinel-2 data and Landsat data being semantically enriched with the SIAM, and then the backend processing of that, and then we have the resources on stack, which then we can quickly analyze with a semantic Python library on a Jupyter notebook. And the interesting bit of this is SIAM is a fully automated physical model, so no training samples. It's an expert knowledge-based decision tree that has been validated. So, and this process can be really fully automated as long as you know how to use semantic and a bit of Python. Then no training is required and things like this. So the semantic library framework, I wouldn't go into it. I will leave some resources, but we have this semantic domain and image domain that is included in an interesting paper by Vandermeer, and I encourage someone who is interested to have a look at that. So for this specific use case, we are trying to look at a semi-arid region in Kenya, where I come from, and they have these arid regions have sand dams in some cases to cope with water scarcity issues and things like this. And a sand dam is just basically a concrete wall built along a seasonal riverbed, and then over the rainy seasons, the sediments collect, and then it's used to kind of store the water over time. So it takes a longer maturity period to have a sand dam fully functionable, maybe 4 rainy seasons, or up to 7 years sometimes. And the kind of focus here was to try to create a buffer around these sand dams to understand the vegetation dynamics in these areas using this semantic EO workflow. And just as a quick overview of the results, for example, this is vegetation intensity, and what it actually represents here, we are representing, it's not really land cover classes that this is vegetation, it's an SIAM output that tells you, hey, this is likely vegetation, and we are representing the number of vegetation observation per pixel, which is represented as a percentage in this case. And the main idea was to kind of compare the outputs between Sentinel-2 and Landsat 8 to kind of see if they are comparable outputs that we can really test this same method, same workflow, just different sensors to see the results if are comparable. And from just an overview of the spatial distribution, keeping in mind the spatial and temporal resolution of the two different data sets, we can have very familiar, very comparable output in terms of, if we look at strong vegetation, for example, the peak percentage observations were quite close, and even the visual distribution of the average vegetation mostly concentrated around sand dams, maybe because of water availability throughout the year, people can still grow stuff, and also the vegetation that is maybe maintained throughout the year. And these are just, can look at the seasonality as well, and quite a similar pattern from the two different data sets. And this is applied for the same time for quite a similar, from 2016 to 2023 for both data sets. And they are quite comparable in terms of the spatial distribution of observation of vegetation observations in this case. And just to have an understanding of what we are looking at in terms of seasonality, if we look at the wet and dry season, for example, and we look at the precipitation, it's very highly correlated. And the patterns are quite similar. It picks up quite similar patterns in terms of the number of percentage of observation in the entire area, and with quite some anomalies. For example, even the peak in 2020, we have both data sets kind of picking that note even in the dry season, because also the precipitation during that dry season of 2020 was a bit high, and maybe some anomalies that maybe events that happened in 2019, which we cannot pick up from Sentinel-2 data. And as a final outlook on the SIAM greenness index, which is more sensitive than NDVI because you get to include also the mid-infrared band, we can see quite similar outputs in patterns in terms of recordings of the greenness index and the peak precipitation and things like this. So as a conclusion and kind of an understanding of the output from the test area, I see the Sentinel-2 and Landsat-8 outputs are very quite comparable, keeping in mind that the same workflow was applied for all of them. The level of automation for the same workflow, as I said, it can be fully automated as long as you know Python and the semantic library, which is open source. And in terms of reproducibility, for example, with SIAM, if we do analyze an image to get SIAM output, this semi-symbolic pixel that are stable, kind of, you get, instead of starting from a spectral perspective, you get to have an interpreted pixel where this tells you that might be vegetation, this is might be water and things like this, and then from there you can build land cover classes. And if we analyze the same scene twice, we get the same output every time with SIAM. So in terms of scalability, for example, for this case, for both data sets, we analyze around 1,200 scenes, and this is very easy to scale up based on the infrastructure that is included. So thank you very much for your attention and for the mentioned resources. For example, the paper with Vandermeer on the semantic querying, and the product that was used, which is Color 33. My colleague Martin has a poster outside, a bit of marketing, so you can visit the booth if you're interested to find out more. And also other papers like for SIAM and the implementation around it. Yeah.
Thank you. Are there any questions? You mentioned, you said that scalability is not an issue from the perspective that you processed already quite a lot of images and seems very fast. I have a question rather from the other side of from the other perspective of scalability, that you tested in the semi-arid region, but if you go now outside of semi-arid region, would you say that it would work the same good, that it would give same results in a different ecosystem?
Yeah, definitely, because, for example, this SIAM algorithm can be applied on any Sentinel scene, and there's a product already implemented from a global scale, so it should be able to work at any ecosystem. Yeah.
I guess I was about the meaning that you were testing in the vegetation can be quite different, and I don't know like how comparable would be if it would be so efficient in some ecosystems where the vegetation is maybe not so clear contrast with other surfaces, like in semi-arid region maybe it's easier than in tropics, but I'm not also expert there, so that's what was.
I think just to maybe provide a bit of clarification, from the SIAM output you can have up to 98 say spectral categories, and with this you can group whichever groups you want. For example, you can have strong vegetation, you can have just deciduous trees and things like this. So you get to actually decide which groupings you want from this spectral representation. Yeah.
Okay. Yeah. Thank you.
Thank you.